So someone asked me about Dijkstras and specifically like more difficult iterations of Dijkstras, like what it looks like when there's a twist or when there's something more complicated going on or it's part of a difficult problem. So I figured I'd just make a little video about it. I'm gonna describe Dijkstras, like the algorithm, quickly because I think most people know how it works and they know how to implement it and what it does. But in my mind, it's important to have a grasp on like the actual mechanisms and the ins and outs of the algorithm and why it works, um, in order to like extrapolate that into more difficult things and like add twists and stuff like that. And then I'll go through a couple problems that are like in my mind pretty emblematic of like modifications that you could put onto a Dijkstra's algorithm. So the basic concept of Dijkstra's is it's just like a shortest path algorithm. So you give some point, let's call it S, and then you want to find for every other point what's the quickest way to get there. So it works with typically weighted graphs, or else you would just use a BFS for an unweighted graph. But it works for weighted graphs, it works for directed graphs, it works for cyclical graphs, it works for disconnected graphs. You would just say, well, these aren't reachable, so that's the answer. The one thing is it doesn't work for negatively weighted graphs, because if you think about it, like what's the quickest way to get from here to here? Well, you're probably just going to want to go back and forth to like lower the distance of your shortest path down to negative infinity. So you would just be like, do that. And that's not useful information. So people don't use it for negative weights. Because if you think about it, like a shortest path problem with negative weights doesn't really mean anything anyway in most cases. So a quick overview of the way it works is, let's say we have like 6, 3, 1, 1, something like this. So you'd say, okay, well, you always have a distance of 0 at yourself, so that's fine. And then you'd say, okay, we'll add in the distance of 3 and the distance of 6. Now, like we've covered this. This has been engulfed by like the component of things that we've like seen and parsed, and we found the quickest way to get to all these things. And now like the greedy formulation of Dijkstra's that's really important is the moment you see something for the first time. So we're about to travel to this 3, or this thing that's a distance of 3 away. The moment we see this vertex, let's call this vertex 1, 2, 3, and 4. The moment we see vertex 2, we will never have a quicker way to get there. And to choose my words wisely, we've added these in. We've added in, okay, go to node 2, go to node 3, try it, see, okay, this takes a distance of 3, this takes a distance of 6. And now it's like, okay, well, now we've done everything we need to do here, and we're at this limbo stage that's like, what's the very next thing we do? Well, we only have 2 options. There's either go to node 2 or go to node 3. And so what I mean when I say the first time we see node 2 is the first time that we're like, okay, we're here now. We've gone here. This is the closest thing to S that we haven't already gone to. We've been adjacent to this node, to node 3, but we haven't gone to it. We've decided, though, there's nothing better to do, so go to node 2. The moment we've done that, we'll never get here quicker than a distance of 3, in less distance than 3. And that's kind of the greedy formulation. So we can just say right here and now, like, the answer to get to node 2 is a distance of 3, always. From this moment on in time, we know that. And then we say, okay, you could go back to node 1 in a distance of 6. Do we want to do that? No. You could go to node 4 in a distance of 4. Do we want to do that? Yeah, right? Like 3 and 1. That seems reasonable. And then we would have something like this, 4 and 6. Let's clean some of this up. Get rid of that. Get rid of that. Yeah, and then what do we do? Now we're here, and we're like, okay, now we know this. We didn't want to go this way. We know that for a fact now. We wanted to go this way. Blah, blah, blah. And then we would eventually go back, and we would say, hey, now we can reach node 3 in a distance of 5, and reach node 3 with a different path in a distance of 6. That's cool. So then we would pop the lowest, and we would say, hey, like greedily, we know now, like this is the nearest thing, because it's the only thing that we haven't actually covered yet. And we can get there in a distance of 5. So we would pop that, and then we would get the 6, and we would say, well, yes, we can also get there in a distance of 6, but too little, too late, it doesn't matter. We already figured out a way to do that. That's the idea behind Dijkstras, or that's Dijkstras. And I think the inner core, the part of it that is interesting and worth returning to, is the greedy formulation and why you can do that. And the best rationale I could give succinctly for why Dijkstra's works and why you can say the moment that I reach node 2 and the moment that this is the earliest thing for me to do, or the closest thing to S I haven't already seen, then I know that that value is exactly the optimal value for node 2. The reason why we can make that greedy formulation is because with the constraints of Dijkstra's, where you can't use a negative weight and you're looking for a shortest path, the distance or the value of a vertex T when you're traversing from S is monotonic with regard to more operations, adding more edges into the path. So if we know right now, let's go back to that snapshot in time when we were looking at node 2 and node 3. And we had in our little priority queue, what was it, 3 and 6? So we're like, okay, we just parsed this, and now we're choosing, do we want to parse this or this? The reason why the greedy formulation works is because we know in this period of time, if we're looking at vertex 2 and we're like, do we want to go into this? Do we want to decide this is a distance of 3? Well, we know right now in this substructure of the problem, this is the nearest thing we haven't covered, right? So the only other options are going to be things that are going to take longer to get to than this. So if we go here, that takes an extra 6 units of time. At that point, we can only increase on our way back to vertex 2 this distance. And so we can just say, like, immediately the moment for this subproblem, this is optimal, then globally this is also optimal. And that sounds like potentially, I mean, yeah, that sounds a little redundant or obvious or just kind of running in circles, but it's important to say these things really explicitly in my mind because it helps when there's a more complicated layer on top or something slightly more complicated is being asked. So I'm going to go through 2 problems now. One of them I'm going to do in Python on LeetCode, and one of them I'm going to do in C++ for AtCoder. Code Forces is down, so maybe there's some good Code Forces problem, but I don't know. Yeah, so skip to the C++ part if you'd rather look at C++ or watch both of them if you like learning about Dijkstras. So path with minimum effort, it's saying, okay, you got this big array and you're starting at the top left corner. You're trying to make it to the bottom right corner. You can traverse from a cell to a neighboring cell, and it's going to cost you the absolute value of the difference. So, okay, fine. But we're not looking for the minimum length path from the top left to the bottom right. We're looking for the minimum max absolute difference on the path. So here, like 1, 3, 5, 3, 5, we never exceed 2. So the answer there would be 2, as opposed to like 1, 2, 2, 2, 5. That would, the sum of absolute differences is lower, but the maximum of absolute differences would be 3, which is higher. So it's not asking just a straightforward Dijkstras that's like, add the next edge, like you're here, this costs 3, okay, add the 1, now you're at 4. Like that would be, more straightforward Dijkstras where you're just taking a sum. But here we're not taking a sum, we're taking a maximum pretty much. And I'll just say right out the gate, like this whole absolute value of differences thing doesn't really matter. The maximum absolute difference, yeah, it doesn't really matter, right? Because we can just kind of translate that really quickly into, well, for any given 2 cells, their maximum absolute difference is just a number. So we can treat every cell like a vertex. There's going to be height times width, or m times n vertices in our graph. All of them will have exactly 4 or 3 or 2 edges, right? A corner has 2 edges. It only has 2 cells next to it. A centerpiece has 4, and a wall has 3. So there's no problems there with like time complexity and number of edges or anything. And we know just exactly what the weights of the edges are. So that works out. Then the problem becomes, okay, there's a graph. It has these weights. Find the minimum maximum absolute difference to get from the top left corner to the bottom right corner. And this is where what I just said a moment ago that maybe seemed a little like pedantic or overly verbose describing something that like already intuitively makes sense. Now we're venturing into a world where it might not intuitively make sense to people. And so that's where it helps to be like, okay, this can bridge the understanding, right? So let's get our vertices. We have edges between all of them. It's a very random way to put the edges in, but works out. And we want to know the shortest path, quote unquote, with this special definition of short. And the thing to recognize here is that, so we're not taking, like, if we have our ordinary Dijkstra's function to assemble all the edges into a path, let's say this is like edges in a path, is going to be equal to like the sum of all the edge weights or something, right? The sum of all the edges. But let's modify that a little bit. Now we're saying this slightly different Dijkstra's formulation is the maximum. This is sloppy handwriting, but it's the maximum edge weight in all the edges. Okay. Well, something I said a moment ago is that, you know, something that makes Dijkstra's work, something that makes a solution to a local subproblem also be a solution to a global problem is the monotonicity. If you traverse through a new edge, you're only ever going to add weight. Or I guess in theory it could be 0, but that doesn't really matter, right? You're only ever going to add weight or keep it the same. So there's an aspect to it that's monotonic. Here, that's the same, because when you're adding non-negative edges, that's monotonic. But when you're taking a maximum, that's also certainly monotonic. The maximum of x and 5 is never going to go down. You're never going to go down by taking the maximum of a number and another number. So we have this same aspect of monotonicity. And that allows us to basically just like copy paste Dijkstra's and change like a couple of lines. So ultimately what we're going to do is say, if you're at some point here, we're going to keep track of, okay, what's your current vertex? I'm just going to keep track of that in terms of I and j. And then we're also going to have like, what's your current distance, but asterisk, right? Because it's not a sum, it's a maximum. And then instead of like, if we go to some new I1, J1 with distance 1, this is just going to be like max of distance and weight. And we know that this is monotonic. And therefore, if this is monotonic, we know that, let's say we have some horizon of things we've already covered. I find that to be like a compelling way to imagine it. If we have some, let's say we've already covered these and now we're like, do we want to go here or what are we doing? We know that we want to take the minimum of whatever of these three we have available to us, because the maximum will only increase it, right? It's the same thing here. When we were choosing between here and here, adding more weights is only going to increase it. Here it's the same thing. Like if this is optimal, taking the maximum to get there through some other means is only going to increase that value. So therefore, if this is already the minimum of these three options, you would just greedily want to do this. Yeah, so this is Dijkstra's, but with a different function, which I actually think is really good problem. This is a great way to like kind of expand it. So I'll just code it out here for the next little bit. Let's see, how do I want to do this? N and M is length of A at 0. Dist is infinity times M for blank in range N. We got to have our heap, which is going to have the distance, which starts at 0, and then the two indices, so 0 and 0. And then I need some auxiliary functions. So I'm going to have max is lambda x and y, x if x is greater than y, else y. This just makes it so that you can't take a max of a list anymore and instantly get the maximum element in a list. You can't. Now this is like, no, it just does this with two numbers. But that makes it a lot faster because in Python this is really slow otherwise. And then we'll have di dj. This is just going to be like, how do you actually navigate to another cell? Like if you're at this 8, how do you know to go to this 3 and this 3 and this 2 and this 2? So I'm going to do like pairwise -1 0 1 0 -1. I think that's what I want. Yeah. Okay, we got the heap, and then while the heap is not empty, distance I and j equals heap pop h, and this is just going to be a lot of Dijkstra's boilerplate. So if distance at I at j is less than d, continue. Okay. For I1, J1 in di dj, no. For di dj in di dj, I1, J1 equals I plus di, j plus dj. Okay. If 0 is less than or equal to I1 is less than n, and 0 is less than or equal to J1 is less than m, then you've found another cell that actually exists. So then we can say, okay, well, distance 1 to get to that cell is going to be the absolute value of a at I at j minus a at I1 at j1. Right? But it's not quite going to be this. It's actually going to be whatever current rolling maximum we have of all of our edges, right? Like it's going to be the maximum of that and this. So d and that. And then we can say, did you find a quicker way to get there? So if we went 1, 2, 2, 2, we're here, and we're trying to get to this 5, we're saying, hey, you have to take a leap of this like absolute value difference of 3. Is that worth it to get to this 5, or was there some faster way? Spoiler alert, there was. So if dist at I1 at J1 is greater than, right, yeah, D1, then dist at I1 at J1 equals D1, heap push H, D1, I1, J1. So then we'll go through, and then it should just be return dist at n-1 at m-1. And we need to account for specifically the 0th, the actual top left, because we never set that. So dist at 0 equals 0. Expected two arguments got 4. Forgot to enclose those. Looks pretty good. There it is. So we pretty much just swapped out one line almost, which was just, well, we swapped out 2 lines. It's actually very important. But we pretty much swapped out one line, I'll say, which was we're not adding anymore. We're taking a maximum. And this absolute value thing, like, I mean, whatever. That's just the way to calculate the edge weight, you know? Just like here, we're not saying like for V in graph at U, like we're not, but it's basically that, right? It's just like a shorthand for find all the adjacent vertices in this graph. This is also effectively just shorthand of like find the edge weight. So this is the one line we're changing. We're changing like an add to a maximum, but there's something else that's actually really important to point out, which is it important to point out? No, that's not important to point out. That's the only thing we're changing. The thing I was going to say that's important to point out is that, no, it doesn't matter. It's that when you're adding, how how do I put this? Yeah, it shows, it doesn't happen to matter, but it does show up here a little bit. You could make the case that this is not quite correct because addition, right? We've identified there's this similarity where they're both monotonic, and that's what matters here. Addition and maximum. But like addition, the identity element, which people usually use E for that, so it's kind of confusing because there's already 3 different types of E's here, but 4 different types of E's. Jesus. All right, well, we'll just add to it. There's 5 now. Like the identity element under addition is 0, right? Like if you add 0 to something, you're not going to get anything different. And I think this is not the most important thing, but it is worth bringing up that the identity element under a maximum, in theory, doesn't really exist, because you could always just have a number that's lower than whatever your supposed identity element was. But the identity element here is basically negative infinity, right? The maximum of anything and a lower number than you'll ever see in the graph is going to be that identity element. Not the most important thing, but worth bringing up anyway, because this is the exact kind of thing where you start to verge on abstract algebraic thinking. And I think that's a really important skill for kind of tinkering with these algorithms. Okay, let's move on to the C++ one. 2 currencies. So N cities, we have basically infinity gold coins, but S silver coins. There's a road that connects city U and V bidirectionally. It costs A at I silver coins and takes B at I minutes. So there's a lot more going on here immediately, is how it would seem. You can't use gold coins, but you can exchange them at any given city to get C at I silver coins. And it takes D at I minutes. So there's a lot of variables. But I feel like their wording almost makes it more confusing than it is. So we have this graph. Something like that, whatever. Where every single edge kind of has 2 weights now. Where we're like, when we're here, we have some, let's call this S again. When we're here, we have some current time that we're at. So let's say it starts at 0. And then we also have, let's not call this S, let's call this U. Because we also have S, which is like some amount of silver coins we have. So let's say like 10. And then when we traverse across an edge, it's going to take us 3 units of time and 10 silver coins. Or what we could do also is not traverse across an edge, but there's this extra thing we get to do, which is just say like increase S and T by a certain amount. So that would be like what C and D are. So So let's say we have like I don't know, 1 and 50, something like that. So we can spend 1 second to increase S by 50. We can spend 1 moment in time to increase S by 50. And then the question is like, what's the earliest way to get to every single vertex? So it feels confusing because it's kind of like Dijkstras, but with like these weird multi-edges, right? There's a lot more going on. It's not just like, what's the weight for an edge? It's like every edge kind of has 2 weights. So how do you decompose this? I would argue that this is a little bit actually orthogonal to Dijkstra's. This is more just like graph theoretical thinking, which is, first things first, forget the gold 10 to 100. That doesn't matter, right? Like that's irrelevant. The only thing it's saying is like we can just see we will never spend 10 to the 100 gold coins. Like we can just look at the constraints and we barely even have to look at them. We can just see this number and go, what they want us to see is that this is completely irrelevant. We don't need to keep track of this. We just need to keep track of how many silver coins we have at any given point. And really C at I doesn't really represent an exchange. It just represents like a rate of increase of silver coins. But we can take that and we can actually make another pretty similar observation, which is that, hey, N only goes up to 50 and M only goes up to 100. This is distracting music. And M only goes up to 100. And A at I only goes up to 50, which is the cost of a given road. So if we had the worst possible case scenario, you would have a linked list of 50 vertices. All of them would cost 50. That's only going to cost you 2,500 at most, right? So there's this like limit we have. That's like you're never going to need more coins than this. And that's pretty important. Because you can treat this as a constraint. Like all of a sudden then what comes into play is like, well, how many coins do I have? How many silver coins do I have? Maybe we don't treat that like distance where it could be 10 million and we need to keep track of it as a value. Maybe we can keep track of it as a vertex, if that makes sense. Like if this were a DP problem, instead of being like, what's the minimum number of coins, blah, 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 10 million, you could say, at this exact number of coins and then calculate that for everything. So that's pretty important. That goes beyond just like simplifying the semantics of the problems, and it actually like is a useful thing here. And I mean, that's pretty much what we're going to do is you can kind of start to see like, okay, well, what if we didn't treat this as we're at vertex U and we have this like value of 10. What if we said, really, there's 10 alternate worlds where we could have been at vertex U, right? Or maybe not 10, maybe 2,500, where we were like, right here, this is where S equals 0. This is where S equals 1, blah, 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 blah. This is where S equals, what am I doing? 2,500. So we just have a bunch of these. And then we say, okay, now like this whole C comma D thing actually kind of works out nicely. Because all we're saying is it takes this amount of time. It's just a new edge. It takes this amount of time to get to a different alternate of the same vertex, right? So what did we have before? It was like 1 comma 60 or something. We could say, okay, well, now we have this random edge here that costs 1 to get from S equals 0 to S equals 60. And then that works out nicely too, because just like before, what did we have, 3 and 10, something like that? Now we can say, you know what, this is actually a lot closer to a normal graph because we have the exact same series of alternate reality kind of vertices here. But now instead of this weird double weighted edge, we can just say, okay, all of these now point to something like S minus 3. Right, so like the top one will point to 57, S equals 57. It'll point to that exact like vertex in this new graph that we're making. And that just has a straight cost of 10. And so with this formulation, like everything starts to fall into place where we can look at this and we can say, okay, from U to V at a cost of A and a distance of B, it's adding an edge from U to V. And we have a way to do that now from any given U comma S to V comma S. And then C and D is very similar. It's just like from U to U again, but like plus a certain amount. I think I'm not gonna code this out because it's kind of, I already did. So I'm just gonna scroll through what I have coded. So let's see, I have distance and I just designate this to be, I mean, it's basically just Dijkstras, but like 2D Dijkstras in a way, where we're looking, our new graph we're looking at isn't the base graph of all the cities. It's this new graph of all the cities for every state. And I just chose 3,000 because that's a big enough number. I don't have to worry about it. So if you're ever above, and this is probably the final like logical piece here before it's just straight implementation. If you're ever above your limit, let's say it wasn't 1 comma 60, it was 1 comma like a billion, because these numbers can get really big. We just say, okay, well then if you were going to go here, don't do that. Just go to the limit instead. So just cap yourself. And then that way there's so many less states you ever have to worry about. So we got distance. That's going to be like actually what we're trying to calculate and what we're going off of. That's like, if you ignore the fact that this is a 2D array, this is just the basis for Dijkstras, just like any other Dijkstras. And we really are just taking a basic sum here of like edge weights, right? Exchange is no matter what edge weight you're at, no matter what vertex you're at, you can always do this. Not this. You can always exchange. So this is just like, these are all the exchange edges. Yeah, so add them into the adjacency list. I keep a rolling calculation of the limit. You wouldn't really even need to for time complexity, but it's just, it's a little bit helpful for like print statements and stuff like that. So you don't print like 3,000 lines with a graph with 2 edges or something like that. We have the exchanges. I build this big priority queue where I say, okay, always be able to get the minimum distance for a given vertex for a given number of silver coins available. And then just always cap that at the limit. The default here is infinity. We're just like set all the distances to infinity, just like regular Dijkstras, because if we can reach it, we can reach it. If it takes longer, then it takes longer, but it'll never take longer than infinity. Set this to 0, and then it's just pretty much regular Dijkstras, but with a couple extra steps here. Here I'm saying if there's any point to actually like doing the exchange, the only time that will happen is if this isn't already at limit. So just keep exchanging up until you get to limit, aka like if we go back to our graph here, like if you're at some vertex and the Dijkstra's greedy formulation does hold, like at any given point, it is invariant that like if we're here and this was the earliest thing we could have gone to that we haven't already seen, like this is the shortest distance to get from you. Well, that is you, so it's a bad example, but like this is the shortest distance to get from you. So then we can say if we have all of our alternate vertices that are just the same vertex in the base graph but with a different S value, then like try jumping to all of these. Or it's really try jumping to one, and then that one will at some point like jump to another. So this calculates the exchange. This is like handling the exchange edge. And then this is handling the regular edges, which are just capped by, can you afford it? Do you have a large enough S, or else this edge doesn't exist from U to V, and S to S minus A, S to S minus the cost. So at this point, it's just a regular Dijkstra's traversal of this like kind of confusingly shaped graph. And then in the end, I just say like, okay, like what's the, for every single vertex, look at the amount of coins you could have had. What was the earliest way to get there? Yeah. And it's just, I mean, once you work out the graph, like how to think about the graph and how to think about what I would call it as the state space. Like once you've worked out how to think about the state space, it becomes just straightforward Dijkstras. And then it's just worth thinking a little bit about like, does this fit in the time complexity? Because what is Dijkstra? It's like V plus E log V, something like that. So here M is the number of edges. The number of vertices we have is what's this? 50 times 50 is going to get us 2,500 for the total amount of S we could ever care about. Times 50 again, because we could be at any S value for any vertex. So we're up to 50 cubed. Okay, so 1E5. Times for each of those, there's 100 edges we could care about. So 1E7, that's kind of fine. Yeah. Looks good. And then I guess there's kind of this theoretical extra like log right here. H dot in place. So I guess we also have like times log 2 of 50 times 50 times 50. So it's getting up there, but 2E8 should still be fine. Especially because this is kind of like a sparse graph, and I don't. Yeah, you can kind of immediately be like nowhere near all of this will be filled up. Yeah, that's the idea here. And then I just coded that up and submitted it, and it worked. So that's a couple extra kind of like more complicated Dijkstras problems. One of them using like slightly different algebra, and one of them kind of requiring a little bit of graph finagling. Hopefully that was helpful.